Hey everybody, it's time to do the Radians. Okay, so this is actually a super important episode if you're going to go on into Math 100. It has to do with your calculator. It has to do with calculus. We'll be going into this in a bunch of detail. But at the end of this, you're going to be able to locate simple angles given in radians on the unit circle. So if I give you an angle, you're going to be able to find it on the unit circle. You're going to be able to convert between degrees and radians, because sometimes it's helpful to go from degrees to radians. You're going to be able to calculate arc length subtended by an angle. You'll know what the word subtended means. And you'll be able to sketch a graph of sine and cosine in radians. So unit circle, arc length, units of angle, circumference, it's all in here. Way to go. Okay. So here's how it goes. On your calculator, take it out. At the top, okay, so here's what mine looks like. 0, and then it says deg. And if it's in deg, that's short for degrees. If I type in sine of 30, I get, hold on, I get 0.5. I can change this to be a different word. There's a mode button I can change, and I can change this so it says rad. If I type sine of 30 when it's in rads, it says minus 0.98803. Okay, so the answer, it's not that this is the wrong answer, it's just that the units for measuring the angles are different. So this is in degrees. This measure of angles is in something called radians. Degrees are old. Not the oldest thing in the world by any means, but fairly old. We're talking Mesopotamia. Right? Babylon. Gilgamesh. Right. So back then, the Babylonian civilization used a base 60 counting system. Our counting system is base 10, so we have separate numbers from 1 till 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Specifically, our numerical, actually, to tell you the truth, English used to be base 12. Which is why there's a separate number for 11 and 12. They both have names. And then 13 is 3 tens. 14 is 4 tens, right? But up till 12, it's its own number system. So the Babylonians had a base 60 counting system. One way to explain that is that we have 10 different numbers, 10 different symbols. 2, 3, 4, 5, 6, 7, 8, 9, 10 different symbols, and we used placements in, so that's units, and then tens, and then hundreds, and we write different symbols in each of these to represent different numbers. Okay. The Babylonians had a base 60 counting system. Instead of 10 basic symbols, they had 60. They didn't actually have 60 different symbols. They had arrangements of symbols that corresponded to 60. But they had a base, essentially, from numbers 1 to 59, they'd fill in this one. And then from numbers that were bigger than 59, they'd fill in this one. So, etc. So we see lots of different counting systems in the world. There's none that's better than any others. Your operating systems use base 16 hexadecimal. Basic computers, CPUs, use zeros and ones, bits. That's base 2. There's just a ton of different bases. Well, why do I keep going on about base 60? It's because the Babylonians were also the first to measure circles. Circles are pretty useful if you're going to do all sorts of geometry, trigonometry. They had their own trigonometry. And if you're going to do it and you want to mark out distances along the circles, they did it in 360 degrees. So this is 60 times 60 bits. And then you do it in tens because that's too many units, and you end up with 360 degrees. Boop, 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 boop. I don't know, whatever. You can draw 360 degrees yourself. And we inherited that from the Babylonians. It's their reason. It's that reason why hours have 30 minutes, and why minutes have hours have 60 minutes, and minutes have 60 seconds. It's all the Babylonians' base 60 counting system. There's an advantage to a base 60 counting system that has to do with decimal expansion. For instance, if you want to write 1 over 3 in terms of decimals in base 10, you end up with 0.33333 continuing. In a base 60 counting system, this type of infinitely long expansion for decimals happens way less often. So, yeah. That's where we get degrees from, is the Babylonians. It's fun, the Assyrians. Anyway, it's pretty old. And the deal is that degrees are old. They're easy to imagine. But that's in part because you're used to them, right? So if somebody goes, oh, hey, this right angle is 90 degrees. Remember what I said about decimal expansions? Right, if it was 10 degrees instead of 90, how would you talk about a third of that? Well, if you're dealing with the Babylonians and this is 90 degrees, then it's really easy to talk about a third of it. That's 30 degrees, right? Yeah, anyway, so long story short, they're old, they're easy to imagine, but they're easy to work with as well. You can subdivide circles into fairly useful parts. So if you're in the pizza business and you want to divide the 360-degree circles, there's lots of different numbers you can divide it by and end up with a whole number of degrees. You divide it by 8, right? 360 divided by 8, 45 degrees, you know? So the long and the short of it is, they're pretty convenient when it comes to illustrating and describing angles. They're not very good at other things. In calculus, when we talk about measuring angles, instead of doing it in degrees, we do it in something called Radian Measure. We don't call it units of radians the way we call it units degrees. We call it Radian Measure. They're a unisless quantity. Don't worry too much about that. Yeah, so the deal is that they're math useful, but imagination gross. Like, so for instance, if somebody goes, hey, there is an angle that's 2 radians, I don't even know how to draw it. I'd be like, I don't know, maybe it's over here on a unit circle. Okay. So, without further ado, let's talk about radians. Specifically, we need to start a problem with a certain type of problem you get in mathematics called the arc length problem. The word arc here, arc usually refers to a curved line. It refers to a circle, a chunk of a circle. So let's start this by looking at a specific problem I've written up. 30-meter radius track. We describe their location in terms of angle theta. What arc length have they traveled if theta is equal to 60? Okay, so this is a typical arc length problem. The idea here is somebody gives you a circle. We specified the radius of the circle is 30 meters. So the deal is that you can talk about somebody running along the circle as having a current angular position. You can specify their position along the circle in terms of an angle. So right now we're saying their current position as they run around the track is 60 degrees. So this arc length problem is asking how long this curved line is. It's actually a super difficult problem to tackle. It's not anything we can do using trigonometry or geometry. So the word arc length corresponds to the length of this line in meters. How do we calculate it? There's a trick, and it's old, but it makes a kind of sense. The idea is we're going to use proportional reasoning. What portion of the circle have they gone around? What percentage of the circle have they gone around? Well, they've gone 60 degrees around a 360 degree circle. So they've gone 1/6 of the way around. 1 divided by 6. 360. So that's 0.166666. That's how far they've gone around the circle as a percentage. A total distance around the circle is 2 pi r. It's the circumference. 2 times pi times 30. So 2 times pi times 30. So it's 188 meters around the circle in total. So if you've gone this percentage around this length circle, then the total distance you've traveled is equal to 0.1666 times the distance around the circle. Percentage around the circle times the circumference. 0.16666 times 188 is equal to 31.3 meters. That's the distance they travel around the circle. That's the answer to this question. Okay, so why don't you let's outline the procedure we used. The procedure goes like this. We're given the angle, the current angular position. We use it to find the percentage distance around the circle. Then we calculate the circumference. And then the arc length is these two numbers multiplied together. Why don't you try a couple questions? So let's try this. the radius is equal to 30 meters. If theta is equal to 180 degrees, find the arc length. R is equal to 40 meters. If theta is equal to 200 degrees, find arc length. And R is equal to 20 meters. If arc length is equal to 80 meters, find theta. Try these questions now. Okay, so let's crack these problems open. First, I want to find the percentage around the circle. That's 180 divided by 360. So that's 0.5. Then I find the circumference of the circle, 2 pi r, and r is 30. So that's 188.4. P times c is equal to 94.2 meters. Let's try it again. The percentage around the circle that I've gone is 200 degrees divided by 360. 0.555. The circumference around the circle is 2 pi r. So it's 2 times pi times 40. So that's 251 meters. P times c is equal to 139.4 meters. All right. This last one's a little bit weirder. So I don't know what P is. I know C is going to be 2 pi times 20. So 2 pi times 20. That's 125.6. And I know that P times C is equal to 80. So P times 125.6 is equal to 80. Well, I guess this makes sense. You think about it as a track. I know the total distance around the track is 125.6. If I know the distance that I've traveled here, which is 80 meters, I guess, then the percentage is just 80 divided by 125.6. So that's 0.636 percentage of the way around the track. And I know that all the way around the circle here is 360 degrees. So the angle divided by 360 is equal to 0.636. So theta is equal to 229 degrees. Okay. So, this whole procedure can be simplified if we think about the algebraic steps involved. Essentially, what we have here is a whole bunch of multiplying and then dividing. And we can boil it down to fewer steps. The arc length is equal to the circumference times the percentage I've gone around, right? The circumference is 2 pi r. It involves me multiplying something I'm given, 2 pi. And then the percentage is the angle divided by 360 degrees, which involves dividing an angle I'm given by some number. I can rewrite this r times 2 pi theta over 360 degrees. following term here is the percentage of the circle that I've gone around times 2 pi. Okay? And we call this number, it's a new number, we call this number the angle in radian measure. Okay? So you start with an angle in degrees. To convert to the angle, the same angular description in radian measure, you multiply it by 2 pi and then divide it by 360. Okay? So radian measure, this is essentially where radian measure comes from. I'll talk about why this is a useful thing in a second. But essentially, radian measure is just another way of describing angles. Okay? So let's imagine we've got a quadrant, a unit circle here. First, let's consider an angle of 90 degrees. Okay? Theta in R is 2 pi times 90 over 360. So it's 2 pi times a quarter, so it's pi over 2. In radian measure, a right angle is given by pi over 2. Now let's consider an angle halfway around. This is an angle 180 degrees. Its value in radian measure is 2 pi times 180 over 360. So it's 2 pi times 1/2, so it's pi. In radian measure, halfway around the circle is given by an angle pi. Oops. Let's go all the way around the circle. That's 360 degrees. In radian measure, 2 pi times 360 divided by 360 is equal to 2 pi. All the way around the circle is 2 pi. Okay, before we go any further, let's practice converting between radians and degrees, or rather degrees and radians, back and forth. The trick here is percentage. What percentage of the circle have I gone around? All the way around the circle. In degrees, it's 360 degrees. In radians, it's 2 pi. Okay? So one easy way to convert back and forth between degrees and radians is to figure out intermediary, how big what percentage of the circle have you gone around? Okay? So if the angle in degrees is 30 degrees, the percentage around the circle is going to be 30 divided by 360. And so the angle in radians is going to be 2 pi times the percentage of the circle I've gone around. 2 pi times 30 over 360. And if you want to, we can write this as pi over 6. An angle 45. Percentage of the round around the circle is 45 divided by 360. That's 1 over 8. Degrees in radians is 2 pi p. So it's going to be 2 pi divided by 8 pi over 4. Try the following. Just calculate the numbers for me. Pi over 6 is 0.52359. Pi over 4 is 0.78539. All right, try these yourselves. (190 degrees). Theta is equal to 250 degrees. Calculate the angle in radians. Another way to think about this is this procedure goes divide by 360, multiply by 2 pi. 100 divided by 360 times 2 times pi. Oh, okay, 160 times 2 times pi. 1.7453. $3.31612. 4.36332. Okay, let's practice going the other way. If somebody gives me the angle in radians, I can calculate the percentage by dividing the number of radians by 2 pi, and then calculating the number of degrees by multiplying 360 by that percentage. So if in radians they give me 2 pi over 3, the percentage is going to be 2 pi over 3 divided by 2 pi, so it's 1 over 3, and the angle in degrees is going to be 360 times 1 over 3, which is 120. 120 degrees. All right. It's not really necessary for you to deal with all these fractions, so try the following. 4, 7, 1.5. Calculate their values in degrees. If you want a shortcut, think about it like this. If you don't want to use the percentage argument, you can divide this number by 2 pi and then multiply it afterwards by 360. 4 divided by 2 pi times 360. 229 degrees. 7. 85.94 degrees. Okay. So let's start by talking about what radian degrees measure. Okay, so ordinary degrees work like this. What you can do to measure things out in ordinary degrees is take a circle, divide it into 6 pieces. So 2 pieces, 4 pieces. Oh, I did that badly. 4 pieces, 6 pieces. and then divide each of these by 60. Cut it into 60 pieces, and the result is 360 degrees all the way around the circle. So essentially that's how you do it. Cut things up in degrees. You have to divide things into a circle into 360. Radian measure is a lot more elegant. If we imagine our unit circle, so if we imagine some circle, big circle here. Hello, I'm a really big circle, and I'm wonderfully drawn. So this is a big circle. And then suppose I want to describe the angular position of this location. What I do is, in radians rather, what I do is I draw the unit circle in the center. The angle in radians is the length of the unit circle between these two. Because think about it. Somebody gives you this distance. We've traveled this distance. That distance is, this distance is 2 pi r around the circle. So it's this percentage around the circle. The circumference of, wait, hold on. Oh, geez. Sorry, I lost my train of thought. This sickness is really messing me up. Okay, so long story short, the radian measures the length, the actual length in centimeters or in meters, whatever, in unitless length of the unit circle. If it's a unit circle is in meters, then its length is in meters. Okay? So we refer to this length as being subtended by this arc. When we see the word subtend, it means we give you this angle, this length, and we want you to find this length. And the interesting thing here is that if you know what this length is in radian measure, the length of this side is going to be depend on how much larger this radius is than the radius of the unit circle. It's going to be proportionately larger, which comes down to this arc length is going to be the length given in radians times the radius. This is why radians are so mathematically convenient. There's some calculus reasons, but at the heart of it, this is what it comes down to. So, in other words, watch as I do it. A runner runs along an r is equal to 30 meter track. If the current position is given in radians, so if it's 4 pi over 7 radians, then the arc length, the distance that he's traveled since he started, is going to be r times theta r. So 4 pi over 7 times 30. $553.85 meters. Yeah? See how easy that is? If I know what the angle is in radians, I can figure its arc length just by multiplying these two together. This is the primary advantage of working in radian measure. Okay, so you're going to see radian measure used exclusively in Math 100. And so one aspect of this that's really important is that we can define the sine and the cosine functions to take the inputs in radian measure instead of in degrees. So in this case, they're going to specify the angle in radian measure. and then calculate sine and cosine. It's not that tricky. Let's try it with our calculators first off. At the start of this, I mentioned that sine of 30 degrees should equal 0.5. Let me check that again. In degrees, sine of 30 is equal to 0.5. When I change my calculator into radians, sine 30 doesn't equal that anymore. It's equal to something else. And the reason is that this angle isn't the same as this angle once you're in radian measure. So let's start by converting this into radian measure. Okay, so if theta is in degrees is 30 degrees, theta in radians is 30 over 360 times 2 pi. So it's going to be going to be 1 over 6 times pi. So if I, which is equal to pi divided by 6, 0.5235998. So if I enter sine of, let's see, so this becomes 0.5235998 0.523598 in radians, you get 0.5. Okay. So what do the graphs of sine and cosine in radian measure look like? Well, let's sketch it. So in degrees, it goes like this. 90, 180, 270, 360, 450, 540, minus 90, minus 180, minus 270, minus 360. So the sine function looks like this. Oh, wait, hold on. All right. The deal with the function when it's written in terms of radians is that it has exactly the same output. It's just that the numbers for the inputs have changed. So instead of 90, which is a quarter of the way around the circle, it's pi over 2. Instead of 180, which is halfway around the circle, it's pi. Instead of 270, which is 3/4 of the way around the circle, it's 3 pi over 2. You know what? I'm going to write this as 2 pi over 2. 360 is 4 pi over 2. This one's 5 pi over 2. This number's 6 pi over 2. This number is minus pi over 2, minus 2 pi over 2, minus 3 pi over 2, minus 4 pi over 2. And that's how you draw the graph of sine. All you have to do is draw the original one and then change the numbers over to be in radians. All right, let's do it for cosine. And then I'll talk about their features. Sketching them in sine, sketching them for sine and cosine is something I probably want you to be able to do to complete this class. All right. 90, 180, 270, 360, 450, 540, minus 90, minus 180, minus 270, minus 360, minus 450. Here's your maximum. Here's your minimum. So cosine looks like this. Minimum here, goes back to 0. Maximum here, goes back to 0. Minimum here. 0. Minimum, 0. Maximum, 0. Okay? So this is cosine of the angle in degrees. And to write it in radians, I'm just going to change these so that it's going up in intervals of pi over 2. 2 pi over 2. 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2. All right, so this is cosine of theta in radians. Okay, I want you to note something fun here. Instead of being periodic over 360 degrees, it's periodic in 2 pi. It's going to have, this is going to be 0 every multiple. So this is sine. Sine is going to be 0 roots when theta is some multiple of pi, some even multiple. So 0 times pi, 1 times pi, 2 times pi, 3 times pi, minus 1 times pi, minus 2 times pi. Similarly, over here, it's periodic over 2 pi. And it has max and min when theta is equal to n times pi. 0 times pi, 1 times pi, 2 times pi, 3 times pi, minus 1 times pi, minus 2 times pi. And it's going to have roots in between. Everything you know about the graphs of sine and cos carry over to this. And in fact, you can think of this graph, cosine in theta radians is equal to cosine theta in degrees if I multiply it by 360 over 2 pi. Wait, did I say that right? Wait, hold on. I mean, this is in degrees, this in radians. Yeah. So you can think of the radians map as scaled degrees. All right, there's one last aspect of this that I kind of want you to be able to do, and only vaguely, is if somebody gives me an angle in radians, I want you to be able to show where it is on the unit circle. This skill is super helpful for you if you're going to be, you know, doing any kind of math. Because we're getting our bearings on the sine and cosines in terms of the unit circles in radians. So if somebody gives us theta is equal to 4 in radians, how are we supposed to interpret that? Well, the idea goes like this. Every quarter circle is pi over 2. So in terms of the angles, this is 1.57, and this one here is 2 pi over 2. So it's just pi 3.14, and this one here is 3 pi over 2, which is 4.7123, and this one's 2 pi, which is 6.2831. Okay? So if you see an angle like this, you can say, oh, it's between 3 and 4, so it's going to be somewhere in this location, somewhere in this quadrant. More often than not, though, when somebody gives you an angle in radians, they'll put it in terms of a mixed fraction like that. And the way to draw these angles is to reduce it so that it is some multiple of pi. Okay? And then what you can do is you can say, okay, this particular angle here is, you cut pi into 3. 1, 2, 3 angles. So pi over 3, something like that. It's not a very good skill, but it's one that's vaguely useful. So why don't you try the following? 7 pi over 4 is equal to 3 pi over 2. Theta is equal to 6 pi over 12. Try sketching these 3 angles, and then you can go. All right, how are we going to do this? Well, you kind of do it the way you do it with angles. You know how when you do it with angles, you break things up into 90-degree chunks? Let's try breaking this up into pi over 2 chunks. 7 pi over 4 is equal to, why don't we call it 4 pi over 4 plus 3 pi over 4. So this is all the way around half, and then this one, let's see, pi over 4 is equal to, like, that's us cutting this thing into 4 segments, so it's 3 of these. So 1, 2, 3. This is 7 pi over 4. 3 pi over 2. 3 pi over 2, you can write this as 2 pi over 2 plus pi over 2. So it's halfway around, and then halfway around like that. So it's this position. 6 pi over 12, huh? Well, this can be reduced to pi over 2, so it's that angle. All right, so it's not a very good, it's not a skill that I think is super important. It's pretty important to be able to convert back and forth between the two, and it's pretty important to sketch a graph of it. But as far as these things go, if somebody gives you an angle in radians and you're really having trouble imagining it, convert it into degrees and then sketch it, just because life is too short. Okay, that's it for this lesson. I'll talk to you guys later. Actually, I won't. This is probably the last video. So congratulations watching all the videos. Talk to you later.